Imagine for a moment a silent, invisible tremor, a cosmic whisper that has traveled across billions of light years. It carries the story of a cataclysm so powerful it shook the fabric of reality. These are gravitational waves, ripples in space-time caused by accelerating massive objects. They travel at the speed of light and carry energy and information from extreme events. The universe is communicating in a language humanity is just learning to read. Scientists have built giant ears on Earth to listen to these whispers. Drop a stone in a pond, ripples spread. Massive accelerating objects do the same to space-time. They tell stories of cosmic birth, life and death. A new sense for humanity. A way to see the unseen and hear the unheard. This idea began with Albert Einstein, who taught that mass and energy warp space-time. Space-time is a dynamic fabric. Bend it, and objects follow those curves. Think of a giant trampoline. A heavy mass makes a dip. Smaller objects roll along curved paths. When massive objects accelerate in asymmetric ways, orbiting or colliding, they send ripples outward. Those disturbances propagate across space, carrying energy away from the source. The loudest events are binary black hole mergers, brief, violent, and visible only to gravitational ears. To understand gravitational waves, humanity must rethink gravity itself. Newton saw gravity as a force pulling objects. Einstein showed that space and time are woven together. Space and time form a four-dimensional continuum. Matter and energy shape that fabric. Place a heavy mass on a trampoline. It creates a dip. Nearby objects follow curved paths, not a direct pull. Planets orbit the sun because they follow the straightest paths through curved spacetime. Geodesics. Earth rolls along a valley in spacetime sculpted by the sun. So, where do the waves come from? They arise when massive objects accelerate through spacetime, causing the fabric to jiggle. Two heavy spheres orbiting create continuous ripples that spread outward. The more massive and faster the objects, the larger the ripples. It is a symphony played on the strings of spacetime. Waves carry energy away, causing binaries to lose energy and spiral together. The final inward spiral creates a crescendo, a short, powerful chirp at merger. That violent moment produces the strongest, most detectable waves. Einstein predicted this behavior long before instruments could hear it. Which cosmic events make spacetime ring like a bell? The universe is full of extreme violence. Cataclysms are primary sources. The most potent sources are massive compact objects, black holes and neutron stars. When two black holes many times the sun's mass orbit each other, they churn spacetime with great force. As they spiral inward, the frequency and intensity grow, a merging crescendo. In the final fraction of a second, they may reach over half the speed of light. In the collision, energy equal to several suns of mass can be radiated as gravitational waves. It is a silent, invisible explosion, lightless but enormous in gravity. Neutron star collisions are another spectacular source. A teaspoon of neutron star matter would weigh billions of tons. These collisions create kilonova flashes. Kilonovae produce both gravitational waves and bright electromagnetic flashes, a multi-messenger moment. Asymmetric supernova collapse can also produce waves. A slightly imperfect spinning neutron star could emit a continuous faint hum, and perhaps the most tantalizing source, a primordial background from the first moments after the Big Bang. Gravitational waves are powerful at their source, but by the time they reach Earth, they are unbelievably faint. They stretch and squeeze space by about 1 part in a billion trillion, roughly 1 in 10 circumflex 21. Detecting that tiny distortion required extraordinary machines, laser interferometers such as LIGO and Virgo. Each LIGO detector has 2 arms, each 4 kilometers long, with lasers split and sent down both arms. Mirrors reflect the beams back. Recombination cancels light under normal conditions. If a gravitational wave passes, it stretches one arm and compresses the other, breaking perfect cancellation. The change is smaller than 1,000th the diameter of a proton, but it is enough to produce a flicker of light. That mismatch creates a signal, a flicker, telling detectors a wave has passed. Having detectors thousands of miles apart is crucial. A true cosmic signal appears at both sites. Local noise from a truck or earthquake affects one site. A cosmic wave affects more than one. Scientists filter out noise, compare detectors, and isolate true events from deep space. On September 14, 2015, humanity heard a clear rising chirp at both LIGO detectors. The signal matched predictions for 2 merging black holes, the first direct detection of gravitational waves. The discovery confirmed Einstein's prediction and opened a new window on the universe. Detection was only the beginning. New observatories will expand the reach of gravitational astronomy. LISA will fly in space with arms millions of kilometers long, tuned to lower frequency waves from supermassive mergers. On the ground, instruments like the Einstein telescope will be more sensitive, reaching further back in time. Gravitational waves let scientists measure black hole masses, spins, and test relativity in extreme gravity. Observing kilonovae showed that neutron-star collisions create heavy elements, gold and platinum. Quick clarification: gravity waves are fluid phenomena. Gravitational waves are ripples in spacetime. By comparing precise waveforms, scientists search for tiny deviations that could reveal new physics. Humanity stands at the dawn of a new age of discovery. The universe is speaking. The invitation is open. Subscribe to our Universal Universe channel for daily cosmic adventures, and don't forget to share and like the video. The cosmos is calling. Together, humanity is learning to listen.